X part of the notes. So, if this is an ice table example, ooh, I did a rice table this time actually. What you just did a reading guide on is it depends on how much of what thing you start with to determine the direction that it goes. So for example, if I started with 2 of these things and 1 of those, we obviously know the reaction has to go in this direction. Because if you don't have any products to get to equilibrium, that makes sense. If, on the other hand, I started with two of these things, well then obviously reaction has to go in that direction. Because again, there's only product, it's going to have to make reactants to get to a balance. However, if I started with a little of everything, that's the point of reaction quotient. And like I've kind of preached throughout the year, the math we do itself isn't tricky, it's just knowing what to do and when. The good news is reaction quotient is the exact same calculation as if you were calculating K. Products over reactants raised to their stoichiometric coefficient. So if I was to do that for this problem, if I were to solve for Q, I'd have 3 squared over 2 times 1 squared. 4.5. Now, there's a couple of ways to analyze this then. You can actually think about what does K and Q mean. They are numerical values of products over reactants. Notice that my Q value is smaller than my K value. That must mean at equilibrium, I have a greater ratio of products per reactants than I do at whatever's happening right now initially, because my Q value is smaller. So that should tell me then that the reaction is going to have to go in this direction. This would have to lose an X. This would have to lose a 2X. This would have to gain a 2X. And then I could do equilibrium math beyond this problem. But there's a couple of ways to kind of analyze K versus Q. And the first one is to think about what is this math? Products over reactants. K is the equilibrium constant, so at equilibrium, this is that ratio. If Q is smaller, that means my numerator needs to be bigger. I need to make more products. Reaction shifts in this direction. Otherwise, if Q is larger, then I have too many products, would be another way to think about that. However, if we can learn some quick little tricks, it might help us out. Now, this is the same information that you wrote down in your reading guide. However, for some reason, textbooks always like to put Q before K when doing these inequalities. I would suggest doing it this direction. First off, K comes before Q alphabetically, so why not? But then, ladies and gentlemen, my gift to you is if you are given a K value and you solve for a Q value and you write it as an inequality, one of these two right here, because again, if they're equal, like my first bullet point, well then it is equilibrium, which I've never seen a problem like that before, because they'll ask you, is it at equilibrium? If not, which direction? Well, it's not at equilibrium. Let's take this inequality for a second. Again, what this says is K is less than Q. Now, we could think about that numerically. And that's what I'm kind of writing in parentheses. You need to make more reactants to lower the Q value. So that's why it shifts to the left. Or, and this only works if you put K before Q, there's the direction that the reaction is going to shift. What if K was greater than Q? Well, that's just like the problem I did on the previous slide. If Q is small, you need to make more products. So you could think about it in that terms. Otherwise, Again, as long as K comes before Q alphabetically, you write it that way. The inequality sign can be treated like an arrow to show you which direction the reaction is going to go. It's just a simple little trick as long as you put K before Q, because if you flip it around, then it's the exact opposite, which I don't know why textbooks always show Q before K. But it's a simple little trick that sometimes will save you, okay, what does this mean? What does this mean? And it's not like I don't want you to think about what your numbers mean, but there's times when you just need to get the problem done. This inequality thing will help out. So the problems that you have done so far, that X that you use to represent change has actually been fairly easy to solve for, because you started off with 0 of one thing and then you knew how much at equilibrium you had of it, so then you could just kind of deduce what X was. There are times that you are not given what is it at equilibrium. And actually this X variable pops up with all things at equilibrium. So it's not as simple as, oh, I started with 0, I ended with 0.45, my X must be, 0.225 or whatever it might be. So what I'm going to go over here is a couple of different ways that we can solve for X when it's not as simple as the problems that we've done. So I have listed a couple of things to consider, and again, what math should I use and when? So sometimes being able to take the square root of everything will help cancel things out to make life a little bit easier for you. Because as I have in all caps at the bottom, we should not have to use the quadratic formula. However, that could be used to figure some of these things out. It should not be needed for us, because another thing that we can do is use an approximation, which is what I mentioned for my second bullet point here. So I'm going to go over a couple of sample problems with you right now and give you time to work on that. Again, I'll give you textbook questions that you can look at, but then you've picked up a slew of handouts as well. One was even on Le Chatelier's principle, so you could go back and practice that some more if you need to as well. But once we get to this step, we've completed our math for this chapter in our book. Again, since we have to skip ahead a chapter or two to finish off equilibrium, you're going to see slightly different options there as well. Okay, here's problem number 1. Again, here's my reaction. I give you the K value, and all that you're given is the starting amount of the HI. So, if I were to solve this, again, first setting up the ICE table here, I would recognize that, hey, the reaction has to go to the left because I only have a product right now. I have to make some reactant and get that balance. So my change for the HI is minus 2x. Again, 2 because the 2 coefficients are from the HI. That means my H2 would gain x, my I2 would gain x. So at equilibrium, I would have x amount of H2, x amount of I2, and 0.25 minus 2x for the HI. Again, very different than what you've been doing before where, hey, you just know the equilibrium for one thing. Next, now that I know my concentrations of everything at equilibrium, I can set that equal to K. K equals products over reactants raised to their stoichiometric coefficients. So 50.2 is my K value. That would equal products, which is 0.25 minus 2x, raised to their coefficient divided by reactants. What's another way of writing x times x? Squared. You have two choices how to solve this, and one is a good choice and one is a very labor-intensive choice. You could multiply both sides by x squared. You could factor this out, and then you could get an x squared, x, and c. Plug it into the quadratic formula because you're not going to be able to factor it out, and then figure out what could x equal. Or we could be a little more clever with our math. And what I notice is this is squared on the numerator, this is squared in the denominator. Why not take the square root of it all? But if I take the square root of one side, I have to take the square root of the other side as well. If I do that, I can give you some of these numbers. Square root of 50.2 is 7.09 equals 0.25 minus 2x over x. Now we have a much simpler expression. Again, our fear in doing any of this equilibrium math, bless you, is x squares. Because now that's a higher level of algebra. That's where, again, it's a little trickier to figure these things out. Here, multiply both sides by x. 7.09x equals 0.25 minus 2x. Add 2x to both sides in order to get your variable on one end. Because if it was a negative 2x there, now it's 9.09x equals 0.25. Divide by 9.09. That gets me an x value of 0.028. Which means, if I were to solve for this and this, it's 0.028. I could plug this into this one. 0.028 times 2, subtract that from the 0.25. And I could get that value as well. Which I actually didn't do on my answer key here. Type it in quick. So as I had written on my answer key all along, it's 0.194. Okay, so that's one method we can do. Again, set up your ICE table. Do like I have in the top of the right-hand corner of the screen. Q equals products over reactants raised to their coefficients. And now evaluate. How can I simplify this in order to solve for x? Because you need to solve for x in order to know what you have at equilibrium. One more problem. You're going to learn in the next unit with acids and bases, there's equilibrium constants. So this is actually the base ammonium hydroxide, how it breaks down into ammonium ion and hydroxide. So my Kb is just the equilibrium constant for a base. So if I give you an initial amount of that, what can I do to solve this? What makes this one a little bit different is notice that there's no coefficients in front of everything. Very common in acid-base chemistry, which again is going to be our next step in the next unit, is doing equilibrium stuff with acids and bases. But obviously the reaction has to go to the right because there's only reactant to start with. So my change is a minus x here, a plus x here, and a plus x there. So at equilibrium I have 0.0075 minus x, x, and x. If I were to set up my products over reactants part now, I'd have 1.8 times 10 to the negative fifth equals products, which is x times x, and I'll just call that x squared, divided by reactants, 0.0075 minus x. So this is the expression we'd have. Unlike the previous problem, I can't take the square root of both sides. My denominator over here, that wouldn't work for. I am not a big fan of multiplying both sides by 0.0075 minus x, because yeah, I could get rid of my denominator then, but I just now have that same issue. I have an x squared, I have an x, and I have a c value. It's not going to work well. Years ago, they used to give us the quadratic formula on AP test because you'd have to use it. However, now, you're allowed to use what we call a shortcut, and that's what I had listed 2 slides ago. That shortcut is based upon you thinking about what do k values actually mean. The magnitude of a k value. If a k value is large, 1,000, 1 million, whatever it might be, that means it's heavily product favored. That means at equilibrium, you're going to have a lot of product and very, very little of reactant. The exact opposite holds true, that if k values are really small, 0.00018, you're going to have very little product per reactant when it comes to equilibrium. So when you think about that, this x value in this particular problem is tiny. Because if the k value, you see a big power, negative power of 10, that x value is going to be tiny. And if it's tiny, a small number multiplied by a small number, x squared, that mathematically can change a lot. But if I take a tiny number and subtract it from 0.0075, it's barely going to change this. Does that make sense? So what our textbook suggests is not messing with the multiplication of x, because when you multiply by either a small or a big number, that can drastically change what you are. But if you subtract or add a tiny number to something, it's basically the same number. So we're going to omit that part. We're going to simplify it. And really, we're just going to deal with this expression instead. Now, this is something we can solve. Now we can multiply both sides by 0.0075. Now we can take the square root of both sides as well. And what we'd get for an x value for this one is 3.67 times 10 to the negative 4th. Or 3.7 if I did 2 sig digs, which is probably what I should have done. Once again, once you get your x value, you can plug it back into your ICE table. But if you think about it, 0.0075 minus that value there, it's going to make it, 0.0072-ish. So it's not going to be much of a change at all. There might be other slight algebraic things that we can do, but the ones that I just showed you, either you're able to kind of take the square root of all of it, like I show on this one, or we use the approximation. These are the 2 most common methods when at equilibrium you don't know anything. And that's what's different today versus what we've done in the past where you've already known stuff. So, between these textbook problems and then the worksheet you picked up on the way in, and again, I just put another Le Chatelier's principle thing, we're halfway down. It's a question that used to be on an old